students, learners, welcome once again for our course Metallocene based catalyst for polymerization. So in the last class, remember we are continuing our discussion on the unique reactivities of the parallel and the bent metallocenes. So today we will continue about the unique reactivities of the bent metallocene, mainly for the group 4 metals. Okay. So in the last class you saw that how the tungsten, tantalum, bent metallocenes undergoes very interesting reactions and plays a important role in as a catalyst in various synthesis. So today I will be continuing the discussion on the reactivities of the bent metallocenes mainly for group 4 metals, and you know that group 4 is titanium, zirconium and hafnium. I will mainly discuss about the titanium and zirconium because the applications of the titanium and zirconium based bent metallocenes are really remarkable in not only just in organics in synthesis in laboratory scale, but also in industries. So as example, like you know that titanium and zirconium based metallocenes are nowadays one of the best catalysts in alpha polymerization. Okay, and that is we will try to learn how it has been evolved, what are the unique properties are responsible for the development of the successful catalysts in alpha polymerization. So let's continue our discussion on the bent titanium and zirconium. This one we discussed in the last classes, but it's a kind of a summary that how what are the basic differences. So in the last class you see that we have discussed about these tantalum compounds. Okay, that one tantalum of the oxidation state, how interesting it is. We also discussed that how the tantalum 3, okay, also like this one, how the chemistry is interesting. We also discussed the W, that is the tungsten, okay, with the D2 electronic configuration, how it undergoes interesting reactivities. Today we will focus mainly on this system, that is the titanium and zirconium. And once again I'll try to remind you that this is the D0 system where there is actually no lone pair. Okay, so no lone pair, and you will see how difference in reactivities of this bent titanium zirconium D0 system from the others. Okay, so let's see its interesting properties. So first we will discuss the Cp2TiCl2, that is actually the D0 system, as I told. Okay, D0 system, and it is 16 valency electrons. Okay, how to synthesize? Very easy, as we have, if you remember the synthesis of the ferrocene. If you take the ferrocene chloride and if you take the sodium Cp, okay, very easily you can get the Cp2 and you get the 2 sodium chloride. So similarly you can synthesize from titanium chloride and 2 equivalent of sodium Cp, and you get your Cp2TiCl2 bent metallocene where 2 titanium chloride bonds are there. And you can also synthesize the Cp2TiCl3, that is 1 Cp ring and 3 chloride bonds using the Cp2TiCl2 and 1 equivalent of titanium tetrachloride. So synthesis is not really difficult. quite easy and straightforward, as you saw for the ferrocene synthesis. Very unique properties once of this one, you will see here that if you do the hydrogenation reactions, that is the reduction, okay, or let's better say hydrogenation, you can get the titanium hydride bonded bent metallocene. Similarly, if you use the alkyl lithium R minus Li plus, so it can easily replace, okay, and you get the your dimethyl titanium metallocenes, and if you use 2 equivalent, you can replace the 2 chlorides very easily, quite easily. Why I am showing? To show that yes, this can undergo the easy substitution reactions, because the titanium chloride bond is quite labile and easily you can substitute, okay, and the bent metallocene moiety is intact. So that means you can functionalize your bent titanium metallocene as you wish. Similarly, if you use the additional 2 Cp minus, you can replace the two chlorides and forms the eta 5 C1. So this is very interesting structure, eta 5 Cp2 and eta 1 Cp2, and here it is titanium, okay. So this is a kind of fluxional, it shows the fluxional behavior. So it always exchange with eta 5, eta 1, eta 1, eta 5. So once one ring is eta 5, it can be converted to eta 1 like that. Okay. So again, it's if you react with any phosphines in presence of the metal, then what happens? It takes the MgCl2, okay, so it acts as a chloride abstracting agent, and in the vacant and the vacant position is coordinated by the phosphines, and you get the titanium phosphine complexes. Okay, so here you see it is +4 oxidation state, here +4 oxidation state, but here you see that it is +2 oxidation state, okay. So again, so D0 become D2 system, okay. Here you see this is, you are taking the AlR3, that is the aluminum alkyl, trialkylated aluminum. It undergoes very interesting reactions where you see that one chloride, so you know that AlR3 is +3 oxidation state, and it always try to take any chloride or extra R group to become the AlX4 minus, okay. So here you see that AlX3 will be like AlX4 minus, okay. So this you see that here this CH2 group, that the methyl group is inserted here and form that compound with the alkylated aluminum. So you can functionalize your bent titanium metallocenes according to use and your applications, and it's quite straightforward. Here you see that if you try to reduce, do the reduction using the sodium amalgam, it undergoes a very interesting reactions. You will see here these 2 Cp rings, that this one and this one undergoes a coupling reactions and form a di-titanoation complexes. Okay, I'll discuss in more detail about this one, and also I'll discuss the chemistry of the titanium Cp2Ti, because this one is really very reactive. Okay, it is very reactive, and this is actually prepared from the Cp2TiCl2 in presence of sodium amalgam. Okay, and this is, you know, this 14 electron system, and it has a D2 electron. So you see that these substitution reactions, these are all actually substitution reactions here, this side, so it's quite straightforward. Okay, and if you do the reduction, that is actually more interesting. So if you take the Cp2 titanium Cl2 and you do the reduction in presence of sodium amalgam, what happen? You get a very reactive, unstable compound. Let's try to find out that what are the difference in electronic arrangement. So Cp2TiCl2, so this is the D0 system, okay, and this is 16 valency electron, and whether in this Cp2Ti you see that this is D2 system because the reduction is happening, and it is 14 valency electron, and it is, you see, coordinatively unsaturated, coordinatively unsaturated. Okay, so this is 14 electrons, and you know that the nitrogen, dinitrogen, it is very non-reactive, very stable. Okay, the nitrogen bond here is almost 946 kilojoule per mole, so it's very small and is a very stable molecule, and is also non-polar, so very difficult to break the N2, and it's a quite challenging process. But here it is so reactive, it can react with the dinitrogen and form the dinitrogen complex. Okay, this is, you will see that is very limited in literature. So what happens? This Cp2 Ti forms dinitrogen complex in both way, like this one and like this way. Okay, in both mode. Okay, so this is actually in equilibrium. Okay, so here you will see that this is quite unique in reactivity, very unique reactions, unique reactions. It can react with dinitrogen and forms a dinitrogen complex. Okay, this is very interesting and very rare. More interestingly, if you see in the last slide, this compound, okay, how this 2 titanium Cp is coupled and form these two CP rings are basically bonded through a carbon-carbon bond and forms a dihydrogen like banana bond like compound. Okay, so how does it happen? So this one undergoes the reduction reactions. Okay, what happens here is titanium, and one is like Cp minus. So this is a Cp minus eta 5 Cp as it is. Okay, and what happens, one Cp, okay, like that. So this is okay. So you will see that it has become eta 4 and the titanium hydrogen 1 bond. Okay, now it is this one, the 2 unit of this, okay, undergoes the coupling reactions between this one. Okay, then what is happening? It is, so basically it is, if you see 2 of this unit forming a coupling reactions. So like this one, okay, and you have a titanium, this Cp, okay, and you see it is a hydride. So here one hydride and one here hydride, and interestingly it forms the titanium hydrogen bond just like a in B2H6. Okay, so it forms like this way. We know that B2H6 we call BHB banana bond, BHB banana bond. So it's like that. Okay, so you know that like that, this is called the banana bond. So here similar, it is forming like this one, and then what happens? It is undergoes the rearrangement, okay, and forms the like your final compound, which is so titanium, and here Cp as it is. Here you have 2 bridged hydrogen bond. Okay, so you see this is the terminal. This terminal is now converted to the two bridged hydrogen bond. Okay, TiHTi. Now what happens here? You have so I think it will be better to write here, not it will be otherwise complicating. So I am writing the structure here. So that it will be more easily understandable. So here you will see that 2 bridged hydrogen bond, here Cp, here Cp, that is eta 5 obviously, and here we will draw the Cp ring. So it's kind of a rearrangement between this one and this one and this one, and you will see here you are getting basically the, if you see the previous, this one you are getting. Okay, so this is very unique in reactivity. So I'll remove this one so that it is easy to understand. So in case here you see that as it is being reduced to D0 to D2 system and becoming a 14 electron system. So what happens here? Here it is undergoing the dimerization reactions between these two units of the eta 5 Cp and eta 4 Cp, and this is basically the carbene, and it's undergoing the coupling reactions and then undergoes the rearrangement. And what is the driving force? Driving force is basically the aromaticity. So it is becoming aromatic, okay, and forming the dimerization through the titanium hydrogen titanium bond. Okay. So this is also very unique in reactions. Okay. So we know now the tantalum chemistry, tungsten chemistry, titanium chemistry. Okay. Now let's go to the zirconium chemistry. How does it differ? Obviously the titanium and zirconium chemistry is very much similar because those are in the group 4 metal. Generally, if the titanium goes one reaction, the zirconium analog also undergoes the same reactions in general. Okay. So let's discuss in more detail. So here you see that if you remember that this one for titanium or zirconium, here metal is either titanium or zirconium case, and in these cases is D0 electron system. If X is halide, okay, or let's say chloride or hydrides, okay, or any R, okay, the alkyls. So what happens? You initially, how many electrons are there? So here is basically the this one electrons and this, so 2 electrons, and then if it is like let's say the 2 halides, like 2 halides, then what will happen? You will see that this one will have and this will have a non-bonding electron pairs. So 1, 2, 3, 4. So these 4 electrons will filled it up, and this one will have the like that, and here you see there is no lone pair, and the non-bonding, this non-bonding orbital will have no electron. So is basically is empty orbital, so that's why it acts as an electron deficient compound. Okay, obviously these are 16 valency electron system. Okay, we now familiar with this one. So this is 16 electron system, D0 system, no electron on the non-bonding electrons, no lone pair. So that's why it is electron deficient compounds. Okay. So these are the group 4, the basic properties of the group 4 metals, bent Metalloceene chemistry, which is quite different, the properties and the reactivities, due to these two reasons. So we'll try to see that how it differs from the other bent Metallocenes what we have discussed so far. Okay, fine. So obviously as there is no lone pair, so this acts as a Lewis acid. Okay, fine. Okay, now we saw that like if it is like molybdenum Cp2 MoCl2. Now you will have it initially it was a d4 electrons. Now you will have two lone pairs. Okay, so one lone pairs. Okay, two electrons in the non-bonding orbitals, and here will become is a Lewis acid. Okay, so extensively we have discussed. Sorry, this will be Lewis base because you have a one lone pair. So we have discussed this electronic arrangement and the criteria in our previous discussion. So now let's see that what the reactions it can undergo considering the electronic factors of this Cp2Zr or Cp2 titanium dichloride compounds. Okay. So as I told, this is electron deficient compounds, and it has a empty orbitals which can act as a pi acceptor orbitals. Okay, so this one can act as a pi acceptor orbitals. Okay, so let's see what can give the extra feature for these Metallocene compounds. Okay, where you have the metal is titanium or zirconium. Okay, mostly now I will be more interested to discuss the chemistry of the zirconium. Okay, so two main applications based on this bent zirconium Metallocene compounds with the structure of this. Okay, the X may be halides or hydrides or alkyls. Okay, one is the like this one. So you have Zr. Okay, so you have a zirconium hydride. I am writing it as this moiety. Okay, this moiety is like this one. Or if you have any alkene, this is alkene. Okay, then you will have this one. Okay, and this hydrogen is basically that one. So it is happening. What is happening? So it's basically insertion of alkene in ZRH bond. Okay, so this is really very interesting other compared to the other complexes, other bent complexes. So another one is, this is actually called the hydrozirconation reactions. So this is called the hydrozirconation process. Another interesting reactions it can undergo, that is the olefin polymerations. Suppose I have this one and this I have the polymer end. Okay, and this is the alkene coordination. So this is the alkene pi complex. Okay, so it undergoes the like that, and here it's my polymer end. Okay. So here what is happening here, you see that again this is a insertion reactions. Okay. So these zirconium bent metallocene compounds are very unique in radioselective insertion of olefin and here the polymerization. And now you can correlate that what properties, electronic arrangement are responsible for these two reactions. Here you will see that as it has empty orbitals, this can coordinate with the alkene which has pi electrons, empty orbitals, and pi acceptor orbital which can act as a pi acceptor. So that means you know that alkene is like that, and it has a pi electrons like this one. Okay. So this is my, is called, can call HOMO. Okay. And it has a pi star like this one. Okay. So pi star is like this one, and this is the pi. So this pi electrons is actually donated to the empty orbital of the zirconation bent metallocene and gives this kind of interesting reactions. And this reactions is basically made this bent metallocene of zirconium popular in industrial applications, because here you see this one is used as to functionalize the olefin, which can undergoes selectively it undergoes the regioselective insertion of the olefin. And second one, this is actually this course is whole about this one, is the polymerization of zirconation metallocene, why it is responsible and why this polymerization reaction undergoes. That's why we discussed about the unique reaction and properties of the bent metallocene, so that we can understand the electronic factors which is actually responsible for undergoing this kind of reactions, which is alkene coordination and the insertion. So as I told that this one is very popular catalyst, that is the Schwarz reagent. Probably I am sure you have heard about that. This is nothing but if you react with or reduce with hydrogenate with lithium aluminum hydride, so you are getting basically the zirconium hydride bond. Okay, example you see here, that's the thing I wrote here. So zirconium hydride complex. Okay, and it has a huge applications. Here you will see that this is hydrogenation reactions. This is called the hydrozirconation reactions, and it is regioselective. And you see that this one is inserted, this zirconium, this alkene is inserted into the zirconium hydrogen bond, and it undergoes then a different substitution reactions and gives a functionalized alkanes. Okay. So this step is very key step, that is the regioselective insertion reactions. and this is very popularly called the Schwarz reagent, that is this one, okay, is used in organic synthesis. You see that how this alkene is converted to different functionalized alkanes. Like if you now once it is you form the zirconium carbon alkylated, that is you see you are basically converting a zirconium and here the chloride and here the R group, okay, and here Cp. So you are converting the hydride to the zirconium alkyl complex and then doing and reacting with like your X2, okay. So that is the any halides, you are basically functionalizing your alkyl. Here it is, you see that is X. If you react with the phosphine chloride, you will get here the phosphine, okay. If you react with carbon monoxide, you will get the formylation here, and if you react with any keto, you will get the acetyl here, okay. So this is very popularly used in organic synthesis for functionalizing the alkene. And another one, as I told, that zirconium complex, that is which is used in polymerization in polymer chemistry. Although this one we will discuss in very detail in the next classes, how does it undergoes. I am just writing you, showing first you have to do the methylation. So that actually do from the zirconium from this one Cp2 Zr Cl2, and you do the alkylation. Alkylation you can do by Grignard reactions or by using the trialkyl aluminum complexes. Then what we do, this one we use the alkyl abstracting agent. Again you can use the trialkyl aluminum and forms the methyl and this one. So you will see there is a vacant position here. So it's basically, now again you see that this is the D0 system. Now it is 14 electron system, valence electron system, okay, here, and this one is actually responsible for olefin polymerization, okay. So this one actually undergoes the olefin polymerization. How? Because you see that if you take the alkene, it has a vacant space and vacant coordination site, so it react like this one and undergoes insertion reactions. So this is alkene coordination. This methyl abstracting step is essential to create the unsaturation, coordinatively unsaturation, because you know that if we don't offer a space for the incoming substrate, then it cannot come to the close proximity of the metal center. So this important, and another important, so it's a dual role important point is that we are putting the cationic charge here, okay. So that means the alkene can coordinate more easily. So feasibility of the alkene coordination will be more if we make the cationic complexes. So two roles why we are abstracting one methyl group, to make a coordinatively unsaturated compound, and also for electronically it is more feasible for the coordination of alkenes, okay. So unsaturated compounds. So now it will go under several insertion reactions and alkene coordination reactions, and then you will get basically the growth of the polymers here, like that, okay, like that, okay. So this is the simplified strategy, the mechanism for the polymerization, how this category of the bent metallocene compounds favors the alkene coordination and alkene insertion, which are the basic key steps for the alpha olefin polymerization. So in these classes we discussed the unique reactivities of bent metallocenes, and now it is very clear that how different in reactivities from the parallel metallocenes compounds, as example like ferrocene, nickelocene, chromocene, like that. And we discussed that how the electronic arrangement, electronic configuration is responsible for reactivities in different fashion. And we saw, by using the simplified molecular orbital diagram, we discussed helps us to explain the reactivity pathway. And then at the last we saw that how the category of the Cp2Z or X2, that is the bent metallocene zirconium, that is the group 4 transition metal compounds, is special from the other bent metallocenes. Although you saw that many of the bent metallocenes of like tungsten, tantalum or titanium are heavily used in catalysis and also in stoichiometric transformation of various organic compounds, which are still used in laboratory scale, and many of these are in industrial scale. So in the next class we will be continuing about the discussion about our polymerization. Now we will enter to the coordination polymerization using the metal catalysts, and we will see that how these the metal catalysts have a special features for making or controlling the tacticity, radioselectivity of the alpha olefin polymerizations. So now students, I am very confident that you will be now able to correlate the electronic factors and the reactivities of the bent metallocenes, and now we will have a very clear idea why bent metallocenes are interesting and why they are so different from the parallel metallocenes. So these are the references you can read, and the last few classes I have taken the content or the discussion from these 3 books. So thank you, and we will see in the next class where we will be entering to the polymerization of the metal catalysts, which are actually the coordination, we call the coordination polymerization. Thank you and see you in the next class.